Okay, so it's April 20th. We are starting another lecture of this hybrid 442-443 course, quantum mechanics and quantum computing. And I just reminded people, especially those who weren't here yesterday, which maybe nobody, that for the next 4 weeks, which is 1/3 remaining of the course, I'm going to strongly differentiate between the two groups. One of them signed up for 42 for 43 by assigning 2 sets of homeworks. And especially those of you who missed some homeworks in the past, you're more than welcome to do both homeworks, and we'll have homework solving office hour sessions. So in principle, if you put in the time, this should all be doable, but you're not required to do both sets of homework. So let's jump in. And also the other thing one thing that I didn't mention yesterday is I noticed that a lot of you are pressed for time. So it's very difficult to find better class times when most of you can participate, but also some of you can stay on a bit longer. So I think I'm not going to be cutting off the lecture at 10 o'clock sharp, but rather if I need like 10, 15 more minutes, I will let it extend. And obviously you're welcome if you have to run off, by all means. Okay, so let's do this. Hang on, this is how I want to do this. Okay. So the idea is, as I already shared with you, I find it useful to write as I speak. So I'm gonna stop sharing my whoops, what just happened? No, I don't want that. I want to create a page here. Okay. Without further ado, let's go. All right, any questions? So actually, by the way, let me just check to see. So I've met, so one of the things that I announced, okay, actually, let me just start writing it. Organizational stuff. Please check if you are in physics 442, whoops, 442 or for physics 443, and do appropriate homeworks. This week. So those of you who are in physics 442, for you, this is homework 6. So I'm still labeling them differently. For physics 443, that's the homework 5 that was assigned last week. Okay. So that's item 1. Item 2 is mandatory office hours to touch base with so that I know where you stand. I think most of you I've spoken with. I think Sabit, Kaya, and Ricardo Renando, we actually talked yesterday. Aaron Navilas, we've talked, I think, last week. Spencer, I don't know what you're up to. So if you want to stay after class and just, so we just touch base, because my worry is that there's this is the time in the semester where everybody is very overwhelmed, including myself, and it's very easy to disengage and then struggle later. So I think it's a good idea to just do a check-in sort of a thing. So I'd like you to, if you can't stay after class, just email me. Anyway, I think I'll stop the organizational stuff here because it's easy to lose track. Good. So there are basic. What is the plan? So today is the today's lecture is aimed at people who are in physics 442, which I think is probably most of you here, if not all. I think this is a nice review also if you have taken for physics, if you have taken physics 442 last spring. You're welcome to stay, and I would love for people to ask questions or compare and contrast to what they already know. So this is what the plan is for the next 4 weeks. So quantum mechanics, basics. By basics, I mean what we usually teach in one semester of undergrad. Okay. So this stuff we covered already, axioms of quantum mechanics. So that means Schrodinger equation plus measurement plus Hilbert space and stuff like that. So this we already covered. Okay. I just want to put it up there because. So then there is this richness of single particle solutions, basically going in and solving the Schrodinger equation. And this is what we need to do today. This is what we're going to start today. The idea is, it's a very simple idea. In physics, we can talk about generalities, that's useful, but it's also extreme. But the way we really learn the subject is by having very concrete special cases. And that's what we're going to work out. And the two things that are totally non-obvious, if you don't roll up your sleeves and get your hands dirty, is that there are very different types of solutions that exist to the Schrodinger equation. Those are bound states. And this is what we need to kind of like have a very firm, concrete understanding. These are bound states, and then that's where, and they lead to finite, discrete superpositions. And all of quantum computing that we have been talking about, is based on that. So the name of the game when you design a quantum computer experimentally is how do we create these bound states that we can control, okay? Now, we haven't talked about that challenge. We just said that suppose we have qubits, let's use them. But this is, how you get that from the real world sort of particles is what is the subject of basic quantum mechanics. Now, the other type of solution, which we're very well familiar with, light and free space, for example, is so-called unbound states. As the name suggests, they're not tethered to anything, they're just running around. And these things are far less controlled. We can emit radiation, but once it's out there, it's out there. We can't capture it. We can sometimes sense a little piece of it. You have an antenna, but they're unbound. They're out there, and they lead to continuous, infinite superpositions. Continuous. How do you say that? Continuous superpositions. Okay. Now, these are very general properties of quantum solutions. And as I said, I think one of the sort of infinite virtues of physics is that there's a distillation to finding very simple examples that you can mathematically solve with no uncertainty. And so that's where the real work of, in a standard quantum mechanics course is to kind of like get students to be comfortable with a few examples. Now, to make these things exactly soluble, we have to distill them to the max, and we distill them usually to one-dimensional motion. right? So and instead of having a real atom in 3 dimensions, we imagine that the universe is 1-dimensional. Okay. And then this is what we're going to do today and in the next lecture, which I may have to record, and you might just have to watch it because I don't know how I'm going to fit twice the lecture amount in the 3 hours that we have managed to reserve in this class. So I will have to get better at recording. And I think I announced yesterday that we now have a YouTube channel, and I've just been like figuring out how to populate it with the recordings we have so far. So all of the recordings are going to be in one place, so you can refer to them, or I can refer to them if I need to instead of sending links. So the way all of these exactly solvable examples work, and this is what we're going to see very soon, is that this is standard machinery that all of you have seen in the differential equations class. So it all boils down to writing some ODEs and worrying a lot about boundary conditions. Okay? So the stuff that we're going to cover today are particle in a box, a box. This is a code word for an infinite well. It's a trap where you just trap particles, and it's in a box because the box is not leaking. So you can see the only way to do this is to have infinities around. Okay. Then there is propagation over and under and without barrier. So these are the two things we're going to do today. Okay. We will probably start a finite square well. And this is really the full, well, you'll see what it's involved. It's basically let me tag it. It's a matching method. Again, this is something that's pretty standard in differential equations, and depending on how rusty you are, this may not be an issue. And finally, the simple harmonic oscillator is sort of, as you might expect based on your physics 120 experience, oscillations are really key in physics. And so the simple harmonic oscillator, which was there in classical mechanics, is going to figure prominently in this sort of a portion of the course. Okay, so this will probably take us this week and next, hopefully maybe a week and a half, but I would say that this is the core of what you would be missing if we just kept plowing through quantum computing stuff. You know, the idea here is to relate, to give you a little bit of a physical background on what qubits are and how that relates to the universe. Now, there are cool things that, especially those of you who might be going to grad school. Okay, so my thing just froze. That's not good. I really hate when it does that. What should I do? I do this a lot. Oh, this is so annoying. Oh boy. Maybe I should go to sleep. Doing that. One second. All right. Oh boy. So, all right, let me do the following. Let me switch to my other computer. I'm going to turn off my video. I'm just going to keep writing until it's tablet comes back to life. Oh wait, it's back to life. Well, I'm going to keep talking whilst I'm rebooting it. So the next set of topics, which are going to be kind of like just giving you a flavor of it, is the approximation tricks that we use in quantum mechanics. Writing as it shut down. Second. See how quickly I can bring it all back together. Come on. One silly internet. One second. Okay. There we go. All right. And oh, that's not good. Somehow it did not. It's interesting. Well, that's really annoying. It did not save the things that I was writing. All right. Today's not my day. All right, let me try to roll with the punches. All right. So I'm missing stuff. Actually, let me just do the following. Let me cheat here. Let me use my prior notes to just show you the outline. Actually, I should have done that. Right. So there are approximation tricks that we'll get a chance to cover. And the more advanced topics, which we will also cover, are what happens to atoms, which live in 3 dimensions. And the most important thing is angular momentum. The quantum mechanics of angular momentum is absolutely crucial. And the last thing is identical particles. Okay, so in the interest of catching up with time, let me play the following game. Let me use my notes, and I'm going to use this highlighting technique to just scroll through it, okay? So there are okay. So the point that I wanted to talk about just very briefly is that we talked about axioms, and some of the axioms are not something that we really do computations with, get results. Like, for example, the first axiom is that, quantum mechanics is defined in Hilbert space. Okay, so it has certain nice properties that they're dot products and whatnot, and we use them, but we don't actually compute anything, so with that axiom that has numbers in them. The axiom that is actually directly relevant to what we do, as far as calculations, is the axiom that says that there's a Schrodinger equation and the dynamics actually follows the Schrodinger equation. So because that begs the question, okay, so here's one particular problem, what is the dynamics, right? And that's work to compute. Because the Schrodinger equation is linear and because the operator, the Hamiltonian operator is Hermitian, as we discussed, we can always write out the exact solution of the Schrodinger equation formally as this decomposition into the so-called eigenstates. Okay. What this discussion is too general. You don't really see anything interesting or rich. As I already said, that there are two different kinds of solutions. And so previously, and we'll see that they're physically very different. Some of them are bound. In other words, they're sort of trapped particles, and some of them are unbound. They're propagating. But even if you didn't know that, if somebody wrote to you this sort of a superposition where there's different states that show up in the superposition with different energies, En, you can see that there's a different kind of dynamical behavior you could contemplate, right? If you have a bunch of oscillations and you want to distinguish oscillations, if the oscillations have a different frequency, you can distinguish them. And that's when you have a gap. So in the technical jargon, the space, the list of energies, En, is called a spectrum. This is borrowed from mathematics. If you have an operator, the eigenvalues of the operator are its spectrum. And so you can talk about the spectral gap, where these eigenvalues are separated by some amount. But as we'll see, and that's the situation if you have states that are bound, say, to an atom, a hydrogen atom, for example, where all of this sort of became, real. People started solving that. But the alternative is to have states that, even though you're writing them as distinct states here, ENs, but they're actually, in some very precise mathematical states, they're indistinguishable. In other words, the different ENs become arbitrarily close to each other as you turn some parameter to 0 or infinity. And that's called gaplessness. Okay. So it turns out that this picture of bound to unbound kind of dichotomy between the types of physical behaviors is accompanied in the spectrum by whether you have, a gap in the spectrum versus not a gap. And this is sort of this is so fundamental to the quantum theory. It's a topic of research in quantum theory of many particles and to present day, right? So I think this kind of a differentiation between gap and gapless is really something you always want to keep in mind. Now, in real terms, what happens is that the frequency that you observe, right? There's this, I just want to remind you that there is this Planck constant, h bar, and it's dimensionful, and it converts frequencies and energies to each other. So the frequency, which I'll remind you is the time it takes to make one full oscillation, is oftentimes traded in for the angular frequency, is how much angle you precess over in one second, per second. And so what you can see is that the frequency is the gap, which is the difference between these energies divided by the Planck constant without the bar, h, whereas h bar is used when you need to get the angular frequency, which is delta divided by h bar. Anyway, this is something that you guys have all seen in physics 240, and I'm just reminding you. Anyway, so now with all of these sort of generalities out of the way, we want to get some actual results. Okay. And so in one dimension, we're going to think of space as being space. It's unbound, infinite. So I have this little comment about, why is the space infinite? It's not philosophy. it's, we may be living in a finite space. Our universe may be in a big box, and we just haven't seen to the edges of the box. We don't believe that, but that's not something we can rule out. But the idea of space being finite is actually a very prominent idea in some of the modern physics sort of theories. It's not true, but when you're writing, when you think theoretically about problems that you haven't solved, positing that space is finite is not crazy. There's something called compactified dimensions. So some of you might have heard that people have wondered that the 3 dimensions in which we live in plus time is not all there is. There are 26 dimensions or 42 or 30, whatever, many dimensions. And one of the reasons we don't see these dimensions because these extra dimensions are finite. So you need special probes to see finite dimensions, it turns out. So if you Google compactified dimensions, you will see scientific papers on this, but this is not what we're interested in this class. Although there is a relationship between compactified dimensions and angular momentum, quantum mechanics of angular momentum, and we'll see that formally. In fact, the motivation for the talk about compactified dimensions comes from that part of elementary quantum mechanics. So anyway, but let's assume that the space is infinite, and we now need to state the problem. What problem we're going to solve, right? The problem here was defined. Let me scroll up. The problem here was defined strictly in terms of H as a matrix. But once we say the space is infinite, how do we deal with that? One approach may be to say, well, it's infinite, but it's kind of like fine-grainedly discretized. And that already gets you thinking about infinite matrices. And this is how people have, if you have done quantum mechanics on computers, for example, they discretize space and they change the level of discretization to see what properties are maintained, what properties are wiped out. But that's not how quantum mechanics was done 100 years ago with pencil and paper. Because, there's a mathematical theory of operators, which is not matrices, right? Operators can be functions, or derivatives are operators as well. So functions on functions can be dealt with using calculus methods, and that's what we're going to follow. But you should know that there are many options, right? So absolutely, if you're gonna, solve, and in fact, on the homework, one of the problems already asks you to do something numerically with quantum mechanics. When you do things on a computer, there's usually no continuum. Anyway, so let's think about operators as functions that operate on functions, right? And so we need to think of what the Hamiltonian is. And again, because 100 years ago, the only thing that people really knew was classical mechanics. They thought, well, we know, how dynamics is generated in classical mechanics. Most of you have taken the dynamics class. So there's this Hamilton operator, which is the kinetic energy plus the potential energy. And it's basically the total energy, right? At any one point, the expectation value of the Hamiltonian is just the energy in the problem. And the classical problem doesn't do anything, but except it generates dynamics. Because the energy is conserved in most classical problems that you guys have seen, the sum of the kinetic plus potential energy is just the total energy. But here we now want to think of them as operators, right? And so in particular, the operator for the potential energy, we'll imagine it as just some function in space, okay? The kinetic energy is a bit trickier. So I'm following the traditional path by which people have arrived at this formulation. And it's not a straight path. I mean, one of the things you learn in Physics 240 is some of the prehistory of how the modern formulation that we're talking about was arrived at. And it was finished in the 30s, in the I think 36, when von Neumann formulated these things. So people already could do quantum calculations even before this way of thinking was formulated. And because the way they've done this is by appealing to classical intuitions. And one of the things from classical mechanics is kinetic energy is p squared over 2f. Okay. Now, to think of P as an operator, it turns out that one has to think of translations, because if you think of what momentum does, if this is a particle, if the particle has momentum, the particle will have moved in a certain amount of time. And so it turns out one can derive that the correct momentum operator is a derivative. Right? So again, for full historical disclosure, this was known in wave dynamics. This was known, not sure if it was known to Newton, but certainly people who came shortly after Newton knew this. Right? In wave dynamics, there's something that we call a wave vector, which is d by dx of a wave. And I think it was de Broglie or somebody like that, who realized essentially by dimensional analysis that momentum and the wave vector are proportional to each other, with the constant proportionality being h bar again. But one can derive this properly, and this is I decided to skip that because I noticed that a lot of elementary textbooks skip that because it's just extra math, and sometimes you just want to accept the definition and see where it goes. Right, so let's accept the definition that the momentum that we should be using is h bar over I d by dx. Okay, let me pause here and see where you guys are. Is this this okay? I mean, a lot of this is, I think, in fact, all of this should be familiar from Physics 240, but I just wanted to see, what am I doing? There we go. I wanted to see if you guys are good. Why did I raise my hand? Or I lower my hand? Oh, there. All right. Very good. Let's continue. Okay. So long story short, two derivatives is second derivative because you basically apply derivative. P squared is P applied twice. Yeah, I hear you. Just a minute. How would I do this? Let me try. So yeah, no, this is going to be a problem because I'm using the other mode. Let's see if that fixes things a little bit. Let's go full screen. How's this? Better? Okay. Well, that's the best I can do anyway. So, okay, I think in the future, I should probably just use a landscape mode all the time, even when I'm writing. Okay. All right, let's keep going. So just to remind you that in quantum mechanics, we use the hat notation to remind ourselves that these are operators or matrices, right? I don't want to say in disguise, but their meaning is, basically in some sense, an operator is a matrix when you're thinking of finite dimensional spaces, right? But the notion of operator is a more general notion. Yeah. Now, it can lead to confusion because there is something that you can define, which is an X operator, which in the basis of positions, it's just X times the ket bra of X, right? And here you can see that I'm using X in three different ways, right? There is the X, maybe I should use my, all the full colors that I have here, right? There is the X, which is just what we would think as a classical X, you know, where am I, right? I'm 1 meter or 1 foot away from the wall, right? So it's a number with dimensions of length. There's another X, which is where I use the first X now as a label for a vector in a, right? So if you think of a lattice of points, right? And if you think that this is point 1, this is another point 2, and this is sort of vector 17, and all of these are individual sort of a basis for this infinite dimensional space. So that's what these X's are. Okay. And the third one, which is the one that's sort of the star of the show right now, is the operator X. Okay. And the idea is that classically, this is the only thing that we ever talk about. We talk about the dynamics of what the position is doing, but the full theory, quantum theory, has, it's really a theory of this sort of a operator X. All right. We'll come back to this. And so I think the point is that if you think of these operators as operating on functions, so this is called the uncertainty relationship, and as you'll see, it's a commutator between X and P, and you can verify this if you think of that there's some function psi of X, and you can ask, how does X and P operate on this function? How do P and X operate on this function? Right. And so X operating on P will be H bar over I D by, I'm already making things messy. Whereas this combination is trickier. D by dx, so that's P, right? Then you're going to operate on X and H, X and psi. And what you'll see is that this, if you take a difference between these, so a commutator between two matrices, you just multiply the matrices in one order minus the product on the other order. And matrices, so for simple numbers commute under multiplication. And the main non-trivial thing about matrices that you learn in linear algebra is that they don't commute because they have structures, and the structures care about which order that the matrix structure can care about which order that you multiply it. And what, if you haven't seen this before, which I mean, again, I'm a little bit nervous that I'm boring you to death here because, Physics 240 covered all of this. But the point is that the non-commutativity of the matrices has a mirror image when you think about how functions operate on how operators operate on functions, right? And so it's like one of these things, if it quacks like a duck and if it walks like a duck, it must be a duck, right? So what I'm trying to say is that, this combination of X and the derivative with respect to X, they don't compute in the way that this more abstract definition does. Anyway, let's I need to hurry up somehow. Long story short, when you go back to this full dynamical discussion, right, you realize that it's really an overkill. You don't really need to discuss all n's. Right, you don't have to treat all of these all at once. You can just pick one of the eigen values and go after that, and that's called the time-independent Schrodinger equation. So the idea is that you basically look for solutions to this equation, and there's no time left anymore because of the time, right? So the idea is that this is the principle of superposition and coming to your help. that if you start the dynamics in an eigenstate, it stays in an eigenstate, and all that it does is that it keeps oscillating. So there's nothing for you to do as far as time dynamics. But there's a lot for you to do to figure out how that eigenstate, what that eigenstate looks like in real space. Okay. And what this is called the time-independent Schrodinger equation is essentially a blown up version of this equation. And so just to put it all together, you don't know what energies are allowed. That's an eigenvalue. So in the matrix version of this problem, you're solving an eigenvalue equation. So you need to find an eigenvalue, you need to find eigenvectors. So the eigenvalue is unknown. And the eigenfunction, phi of n, is also unknown. Okay. All right. Questions about this? This is all there is to say about the general setup. Okay. There's no more, no less. Okay. This is good. All right, I'd say it's good. There's five people are saying it's good. So let's go. 4 or 5. Yeah. All right. Let's end this poll. All right. Let's see. So the I think all books essentially start with this example, which is the simplest, mathematically simplest case, which is, what was that equation before? Which, this equation? Well, this is called the, yeah, so this is called the time-independent Schrodinger equation. Right, so the Schrodinger equation is the thing that tells you how things moves in time. So the full Schrodinger equation would be this thing with this replaced with I d by dt sine. But what I'm saying is that if you agree to talk about one eigenstate at a time, then all of the time dynamics, right, is so simple. You can see visually how if you operate with a time derivative on this guy, you'll just get En down, and these exponents will cancel off here. You know what, since there's a question, let me just do all of the extra work. The point is that all of the, exponentials are your friends because derivatives just pass right through them, right? The point is that if you apply a time derivative to something like this, all that it does is it brings down En here, and so then you can go through and cancel the exponentials from everywhere, okay? So the idea is, well, let me just, instead of asking whether that makes sense, just repeat it. The idea is that instead of taking the most general case, we want to decompose it into one at a time and solve it one eigenstate at a time. Okay. Is that okay? All right. Let's just keep going. Oops. All right. So, right. So the particle in the box sort of problem is basically saying that let's create a potential that is as simple as it can be. In other words, it's zero, except when it's infinite, so that to confine the particle motion to here, right, somewhere here. Right, so we don't let it to leak out anywhere, but it's just going to be here. It turns out the only way to do that is to crank up the potential to be infinite everywhere we don't want it to be, and then here the potential is zero. Okay, so so here are the steps, and these are the same steps. No matter what problem you're having to tackle, the steps are identical. right? So this is one of these sort of cases where you're learning how to do this simply by repetition. And every case will be slightly different, slightly more difficult, but the steps are the same. Okay. The idea is that we're looking for finite energy solutions. So if we think back to, I should have copied the equation. Well, let me copy the equation here. Oops. I'm going to bring the potential on this side and leave the derivatives. Okay. So we're looking for finite energy solutions because I think infinities in physics have a bad reputation. Like the real world doesn't have infinities. In the sense that 0 is 1 over infinity, real world also doesn't have zeros. Right? I think zeros and infinities are just mathematical abstractions. I think you should just internalize that at the level where you don't even think about it. Okay. Because we're interested in finite energy solutions, usually, always, the fact that we cooked up a problem that it has an infinity, right? I should put infinity in quotation marks because of what I just told you. That means that the only way, if you look at this equation, the only way to satisfy this equation out here is for this to be neutralized by saying that, well, the potential is, your function, your value of the function will have to be 0 outside. So we're going to we're going to be looking for solutions that vanish where the potential is infinite. And again, one of these sort of a physics sort of a common understanding is that infinity times 0 in this case is 0. Or it can be anything you want, right? As you'll see. But basically, we want to not think about that. Now, inside the well, the potential is 0. Again, we don't think about it. And so the equation that we have to solve inside the well is this very friendly equation. This very friendly equation has simple solutions, which is superposition of plane wave going this way or that way, or if you prefer sines and cosines, it's superposition of sine and cosine. It's up to you. The important thing is that the k that you get is essentially a proxy for what the energy is, right? Because k squared is 2me over h bar squared. Again, all of this should be familiar from Physics 240, just going through this. Now, the thing that you should appreciate, you should always be on the lookout. You should count things that you've solved for and things that are still, unknown, right? This is the way differential equations work, because you oftentimes have some floppy bits in the solution that have to be fixed by some additional information. And so far, you don't know what k is. You just know it's related to the energy. And you don't know what these amplitudes of plus and minus k are. So there are 3 things that you don't know still. Right? You don't know most things. Well, okay, as I already said, phi has to be vanishing at the outside of this. And as we'll discuss more, the solution should be continuous across that boundary. And so that just means that the solutions we're looking for, they look like sines and cosines that fit inside the box, okay? And if I put my origin in the middle of the box, the solutions that are allowed are, I've written a few of them here. They're cosine, that's the first one. This one looks like a sine. And you can see that, you just have to check that you choose your coefficients underneath sines and cosines in such a way that they vanish. And what you find is that you can look at this, right? Ignore whether it's a sine or cosine, right? Just pay attention to this. What you see is the coefficient of x which is essentially what K is, right? So they're always either sines or cosines of K and X, right? By looking at this, you can see that Kn is following a certain pattern, right? So the first allowed thing is a cosine. The next one is a sine, but they're all stepping up as integers, okay? Because this one is pi over 2a, this is 2 pi over 2a, this is 3 pi over 2a, and so on and so forth. Now, why did I choose this ordering 1, 2, 3? Now, it's not just that, because what you realize is that because of this property, that k squared and the energy are essentially proxies of each other, you know that the energies are growing proportional to n squared, because energy is k squared, essentially, with various coefficients. This is the equation for the energy. So right there and then, you've solved for what the spectrum is. Now, if you look at this set of functions, you also actually know what a plus divided by a minus is. That's either plus or minus 1, depending on whether it's a cosine or sine, okay? So energy you solved, the relative ratio of a plus and minus you've solved. The only thing that's left is the overall magnitude of a plus and minus, and that can be deduced by demanding that these wave functions are normalized. Remember that there was this fundamental sort of a meaning of the wave function in quantum mechanics, that it squares the probability. And so phi n squared is the probability that the particle is at this x, or that x, or third x. And what we know is that the particle has to be somewhere inside the box. There's one particle and somewhere inside the box. So the integral of phi n squared has to be 1. Okay, well, it's a small exercise to just check that. That means that the absolute value of a plus, a minus, and a minus is 1 over square root of a, and the relative, as I said, the relative sign is here. Okay. Anyway, so putting all this together, this is the answer. Well, in fact, let me box all of it together. That's easier, fewer boxes. Okay. So you can see what the steps are. The steps are, you want to, and these are sort of standard steps in differential equations. You want to figure out what the allowed basis set is for the solutions. In this case, it's just plane waves parameterized by the wave vector k. Then you want to figure out how the boundary conditions constrain your solution, because if there are more than one solutions that can contribute, these a plus, a minuses are not constrained. Anyway, all right, is this clear? Oh my God, it's 10 o'clock already. Okay, if it's clear, let me. Oh, somebody said something. Okay. All right, let's keep moving. So this is an example. You can see that, because, n squared, n plus 1 squared minus n squared, is, what is it, 2n plus 1, right? This is always finite. In fact, it's growing. And so this is an example of a gapped spectrum. Okay. But there's actually an extra, there's a wrinkle here that we can exploit to get a handle on the gapless spectrum. In the gapless spectrum, you expect when the amount of space in which you're moving is truly infinite, right? Because here I gave a little spiel about space being infinite, but what is the first thing I do is I just go and block most of it, right? And that's usually how we go about, building up our understanding, is that we want to kind of like work somewhere small and then expand our horizon, so to say. So now if we want to study problems in free space, you can ask yourself, well, can I just lift all of these steps into free space. And sure enough, the first step, the step where you say that, well, if there's no potential, the solutions are just plane waves and the energy is that seems legit. It's just a second derivative. And so, but that's all you have. Right? So that means that in free space, the conditions on K just do not exist. K can be anything you want, right? In particular, if you take two Ks and you ask what is the energy of the first plane wave, EK1, and the second plane wave is EK2, the difference can be arbitrarily small. So this is an example of a gapless spectrum, as one would expect. But that's not all, right? Because now the question is that, well, what happens to the wave functions in the normalization? And here we run into a problem where the usual prescription that the integral of phi squared dx has to be 1 is just impossible, because if you have a plane wave, right, if it's this object, if you take a square of it, I mean, it's kind of finite everywhere in space. So how can the integral be 1? And clearly this is sort of this is a nuisance. Free space exists, particles exist. So this is one of the sort of a philosophical, if you like, questions, right? So if you have a theory and it says that, oh, you have to follow these steps, you have to normalize all the solutions. And at some point the theory says, well, you can't do that in free space, but then you think that, well, no, but the theory has to work, right? So you just have to relax a little bit about certain requirements. But you can also think of free space as just a really big box, as I already said. So let's actually go through the math, right? The power of physics is to make sense of things that seem to be just outside of what you've just defined by using math, right, as usual. And the point is that, so here we have an idea that we can think of free space as not free space, but just a really big cage, big box. That means that let's just go back to all the formulas that we had before, right? In particular, let's take the formula for the spectrum of particles in the box. And now we're going to think about, okay, suppose we want that to look like the free space spectrum. And as we already noted in the first example, well, the discretization, the mandated discretization of particle in the box states is this one. And so sure enough, you can relate these three boxes by basically saying, well, yeah, if A goes to infinity, then the discretization of particle in the box states just disappears, right? The different K's become arbitrarily close to each other, and we recover the continuum nature of free space K. All right, so that's at the level of energies, there's nothing else to say, we're done. Now, at the level of normalization, remember the normalization before was 1 over root size of the box. And so now what we can see is that if you use this normalization here, because things were normalized, they remain normalized. But that basically means that the individual solutions with this normalization are going to be funny. They're going to have vanishing normalization, but it turns out that it's okay as long as you compute all of them. Like when you, as we'll discuss, there are ways, unfortunately, I'm not. I was hoping to cover enough so you guys could start doing the homework. I think this is taking too long, so I'm going to have to record a separate lecture and expect you guys to watch it before starting the homework. So I think this is a good place to stop, because I have some words here that I've already said that, basically you can think of this normalization as a flexible tool, right? Because if you take it literally, if you take the normalization literally, it's basically requiring for you to be talking about one particle. So if you have one particle in infinite space, then, you know, it's hard to keep track of it. So oftentimes people, if the amount of space they're dealing with is infinite, well, maybe the number of particles should be scaled with the volume, right? So this is kind of like going back to like physicality of our existence, that we generally don't talk about one particle in the universe. We talk about the finite density of particles in the universe. And, you know, the way this shows up is that this overall normalization drops out of real calculations. All right, I think we should stop here, and I'm just going to have to figure out how to take some of this and make it asynchronous by recording sessions by myself and posting them. I'll work on that today. Today is Tuesday, so I think before tomorrow we will find out if I can actually do that, because that way we can differentiate and have multiple homework streams, because otherwise I would have to do something else if I can't record. Okay, any questions? Okay.
Not for me.
Not okay, good. Well, good or bad. Let me just make sure I have the yeah, I'm gonna send an email with the homework anyway, but let me just see if I can, if I still have that stream. There we go. So you guys should start looking at this homework. It probably makes sense to wait until I post the rest of the lectures. Hopefully by the end of today. Okay. And tomorrow, I think I'll probably do, I have to decide whether to lecture on quantum mechanics, quantum computing tomorrow. Yeah, anyway, work in progress. We'll get there. Let's see. So one of the things that I want to make sure is I have all of your proposals for the paper. So let me see if anybody who is on the meeting now, if they've all submitted the proposals. I have this roster, class roster. So let's see. So yeah, no, I don't. I think all of you guys submit. Oh no, Winston is here. Yay, Winston, you're missing your proposal. Do you mind staying after class to discuss a little bit? So you and Spencer can take turns. Anyway, we're done with the lecture. I'm gonna stop the recording unless there are questions. But as I said, those of you